Handling effects. The consequences of ice accretion on the wing and tail surfaces are immediate if the aircraft anti-icing system is not used. Lift is reduced, drag is increased, stall speeds can increase, and the aircraft pitching moment may change. Let's take a few moments to carefully consider the effect on aircraft handling. In flight, ice will normally accrete in areas around the aerodynamic stagnation point. If ice droplets are big enough, they will strike the wing farther aft, creating a variety of shapes, thicknesses, and textures of ice, effectively changing its shape. Changing the shape of the airfoil will change the airfoil geometry to produce a new airfoil in which the lift, drag, and pitching moment characteristics are different from the wing's designed airfoil. Check the lift curves shown for an airfoil with ice and without ice. Compare the curves and observe the reduction in lift at a given angle of attack and the reduction in maximum lift angle of attack. For example, for a wing covered with insignificant rime ice, only a ½ millimeter thick, the maximum lift capacity decreases 33%, and the critical angle of attack is reduced, in this case, from 13 to 7%. This shows the degree of potential hazard from a relatively small amount of ice on an aircraft wing. Ice causes a similar effect on drag. Drag varies greatly from almost no increase to a more typical 100% increase, resulting from rime ice, and 200 to 300% for clear or glaze ice. The overall effect of ice accumulation on the wing is quite obvious. If the aircraft anti-icing system is not used, ice accretion can increase stall speed, resulting in a potential for a premature stall at a lower angle of attack. To cope with the situation, the Embraer Regional Jet stall warning system is triggered at a lower AOA in icing conditions. This protection is automatically activated when ice is sensed by the ice detectors and is displayed to the pilots by a dedicated ACUS message. Ice Protection System Overview. A brief review of the aircraft's ice protection system might be appropriate at this time in our presentation. Ice is detected by two sensors located on the nose of the aircraft. Once ice is detected, a signal is generated to turn on automatically the wing, stabilizer, and engine anti-icing systems. This signal is inhibited on the ground for wheel speeds below 25 knots. An advisory ice condition message appears on the ACUS if ice is detected. The override switch, when selected to all, allows the flight crew to bypass the ice detectors and manually turn on all ice protection systems, provided that the airplane is airborne or wheel speed is above 25 knots on the ground. Selecting Auto allows automatic operation of the system. Selecting ENG turns on the engine anti-ice protection system and maintains the remaining system operating under automatic logic. A test knob to perform a system test is also included. Wing anti-icing operates only in flight or when wheel speed is above 25 knots on the ground. Operation is controlled from the cockpit by a button which closes the wing anti-ice valve when it is released, or allows automatic operation when it is pressed. An open light illuminates in the button to indicate that the anti-ice valves are manually or automatically commanded to open. When the valves are open, adequate bleed airflow is supplied for ice protection. Hot bleed air is ducted along the wing's leading edge by piccolo tubes, flowing through perforations to heat the surface. The same concept is applied to the horizontal stabilizer leading edge. The engine anti-ice system may be operated on the ground or in flight. When the system is on, the anti-ice valve is open, which allows hot air from the engine high-pressure port to be supplied to cowlit. The windshields are electrically heated for anti-icing and anti-fogging purposes. The system should be selected on whenever outside air temperature is below 10 degrees Celsius. Sensors are heated according to a dedicated logic. Pitot 1 and 2 and Pitot Static 3. AOA 1 and 2, ADS static ports 1, 2, 3, and 4. And pressurization static ports are heated whenever at least one engine is running. Pitot Static 3 and Pressurization System Static Port 2 are heated whenever the aircraft is airborne. TAT-1 and 2 are heated when associated engine anti-icing system is on and thrust lever angle is greater than 65 degrees, or whenever the aircraft is in flight. Anti-ice and de-ice fluids. When aircraft surfaces are contaminated by frozen precipitation or frost, before departure, they must be de-iced. When the risk of freezing precipitation exists at dispatch, or freezing precipitation is actually taking place, the aircraft must be anti-iced. While de-icing removes ice, anti-icing protects against additional icing for a certain period of time called holdover time. A combination of both anti-icing and de-icing may be performed based on the judgment of the flight crew and procedures developed by the operator. De-icing and anti-icing fluids lower the freezing point of frozen precipitation, thus delaying the accumulation of contamination on the aircraft. When applied to a clean surface, the fluid forms a thin layer that has a lower freezing point in precipitation. The fluid is highly soluble in water. Thus, the precipitation, or ice, melts on contact with the fluid. These fluids also delay the onset of frost on aircraft surfaces. As the ice melts, the fluid dilutes with the water, thereby causing the mixture to become less effective or to run off. Ice can begin to form again after enough dilution has occurred and freezing point begins to rise. De-ice, anti-ice fluids are not intended to provide icing protection during flight. The fluids must flow off the surface during takeoff, or they may cause undesirable performance effects. Embraer performed flight tests to investigate the effects of approved fluids on performance and handling characteristics. The tests demonstrated that these fluids did not have a measurable effect on takeoff and climb performance. Fluids are generally mixtures of glycol, water, inhibitors, thickening agents, and wetting agents. Glycol lowers the freezing point and prevents the formation of ice contamination at temperatures below freezing. The wetting agent allows the fluid to conform to the aircraft's surfaces. The inhibitors prevent corrosion and increase the flash point. The thickening agent, normally propylene glycol with polymers, enables the coating of fluid to remain on aircraft surfaces for longer periods. Type 1 fluid is unthickened, while fluids from type 2 to 4 are thickened. Type 1 fluid characteristically forms a thin wetting film which provides relatively limited holdover time and provides protection against refreezing when no precipitation is present. Type 1 fluid is normally pink or reddish-orange in color and is diluted with water to result in a freezing point approximately 10 degrees Celsius below ambient temperature. No additional holdover time is provided by increasing the concentration of fluid in the fluid-water mixture. Fluids types 2 and 4 form a thicker film that provides a longer holdover time. By increasing the concentration of fluids 2 and 4 in the fluid-water mixture, additional holdover time is provided. Fluid type 2 is normally straw-colored, and type 4 is green. Type 4 is an enhanced performance fluid with anti-icing effectiveness superior to type 2 and increased holdover time. Similarly, Type 2 is more efficient than Type 1 fluids. Type 2 and 4 fluids offer significant operational advantages in terms of holdover times. However, thickened fluids may dry out during flight, and residues may form in aerodynamically quiet areas. The residues may turn to a gel, which can freeze in flight, potentially restricting the movement of flight controls. Such an occurrence has never been reported on an Embraer regional jet. However, operators are reminded to frequently inspect control surfaces, gaps, and tab hinges for signs of residual gel. If an approved fluid shows to be subject to gelling, poor water wash-off, or unusual dry-out, Embraer should receive a report of the occurrence. De-icing fluid is composed of heated water or a mixture of water and Type 1, 2, and 4 fluids. Heating is applied to a minimum temperature of 60 degrees Celsius. To assure maximum de-icing efficiency, anti-icing fluids include all fluid types in a mixture with water or undiluted. The use of holdover times.